Hello, everyone. Thanks for joining us today. My name is Kristen Vandewaal, Regional Vice President of Sales for the West and Midwest. I'll be your host for today's webinar titled The Key to the Right Cable, Kerite, Benefits and Applications. Kerite has been manufacturing and installing EPR cable for over 150 years. This presentation will focus on why the Kerite design is unique in the industry, the benefits this solution provides, and the various applications Kerite is well suited for. We'll also discuss trade-offs to consider when specifying cable, with special emphasis on 105 and 90 degrees C operating temperatures. For today's format, we'll start with a 60-minute PowerPoint presentation, and we'll follow that with a Q&A session. The presenter will take breaks throughout the presentation, though, to ask for questions. Please use the Q&A tab to submit your questions and not the chat feature. Anyone who submits a question that we don't get a chance to get to, we'll send you a response in writing. Also, there will be a brief 3-question survey that pops up in your browser at the end of the webinar, and we greatly appreciate your response. Now I'd like to introduce you to today's presenter, Matthew Kubikowski. Matthew is the design engineer for 5 to 69 kV medium and high voltage cables at Marmon Utility. He's responsible for the product design and technical support for both TRXL-PE and DR-EPR insulated constructions. He's a member of IEEE and has been part of the wire and cable industry for 2.5 years, all of which have been in a product engineering capacity. Prior to joining Marmon Utility, Matthew spent his career as a product design engineer in the Silicon Slopes startup industry in Utah. Matthew earned his degree of physics from City College of New York, and now I'd like to turn things over to you, Matthew.
Thanks, Kristen. Good afternoon, everybody. As Kristen alluded to, I'm going to discuss the key to the right cable, Kerite, benefits and applications. Brief overview of our agenda today. I'm going to introduce us and who we are, talk about Kerite as a whole, a little bit about what makes Kerite stand out, and then wrap it all up in a nice bow for everyone. A little background: Kerite was founded in 1854 by Austin Goodyear Day. He's the nephew of Charles Goodyear, of the vulcanized rubber founder. We have a long history in power cable and wiring cable. In 1865, we introduced the crosshead extruder to the industry, and we have a long history of subsea cable. The other part of Marmon Utility on the power cable side is Hendrix. We're not going to cover Hendrix a lot today, but I do want to introduce them as they are part of the Marmon Utility family. Famously introduced the aerial spacer cable in 1952, and has installations in over 75 countries in all 7 continents. Marmon Utility today, we have 3 facilities in the Northeast. In Seymour, Connecticut is our Kerite plant making the discharge resistant EPR. In Amherst, New Hampshire, we have our molded overhead products. And in Milford, New Hampshire, we make our overhead and underground TRXL-PE products. Now, the typical extruded power cable looks something like this on your screen right here. Starting from the inside out, we have a conductor, usually aluminum or copper. Following that, we have an extruded conductor stress control layer. This is typically semiconducting, but can be non-conducting, which we will get into later. Following that, we have our extruded dielectric insulation, our extruded insulation shield, referred to as a semicon, a metallic shield, and a jacket. Now, a little bit about what is the stress control layer, right? Now, this is the first barrier against stress. This layer is intended to even out the stress generated through a conductor. And then going into the insulation layer, this is extruded solid dielectric. This is the insulating layer that does most of the magic inside of a power cable. It insulates against other conductors and other conductors conducting parts of the cable. And it's designed to withstand the electrical stresses as well as handle thermal loads throughout operation. A common issue with insulation is the presence of partial discharge, also known as corona discharge. So partial discharge is when there are voids present in your solid dielectric. An electric field ionizes there and creates breakdown pulses in those voids, and in turn degrades that material over time. So there are 2 design theories when it comes to insulation, one being discharge free and one is discharge resistant. discharge free, which is going to be your TRXLPEs, XLPEs, typical EPRs, EAM installations. Those allow up to 5 picocoulombs of partial discharge within the material to be considered discharge free. This is dictated by the industry standards such as ICEA, AEIC. There's another installation type theory, and that's discharge resistant. This is where Kerite falls. This material is immune to the effects of partial discharge. It does not break down in the presence of partial discharge. It is classified as as discharge resistant through an ASTM test D2275, and currently only includes Kerite DR-EPR installation. Moving along, we have the insulation shield layer. That is again another extruded layer that is semiconducting over the insulation. It confines the electric field within the insulation layer, symmetrically again trying to evenly distribute those voltage stresses while minimizing surface discharge. Now more about Kerite. Kerite's main offering lies between 5 and 69 kV. We have a typical aluminum and copper conductors. Our conductor shield, as I mentioned earlier, is a non-conductive PermaShield. Our insulation is the discharge-resistant EPR I was just speaking about. We have 2 options for insulation shield. Noted here is our extruded free stripping semiconducting layer. We also have a more commonly found thermoset insulation shield. For metallic shields, we offer round, flat strap, copper tape. We have a wide variety of jackets, and we also have some specialized options as well, which I'll get into more later, but PILC replacement being a main one, pre-assembled aerial cable, CIC, etc. Now, what makes Kerite stand out? Summarized here, right? We saw earlier a typical power cable breakdown. Here is the Kerite power cable breakdown. Again, we have our conductor just like any other power cable, but moving on to the conductor shield layer, this is the first place where Kerite stands out. We have the Kerite PermaShield. This is a non-conductive stress control layer. Following that, we have Kerite's discharge-resistant EPR, and then Kerite's free strip insulation shield that's thermoplastic. Getting into some more depth about the PermaShield layer, first introduced to Kerite in 1958, where it was first commercially available. It's a non-conducting stress control layer. This material is recognized by both AEIC and ICEA. Due to the fact that it is non-conducting, it allows us to have 100% continuous inline production testing. This is a spark test with 2 kV DC attempting to break through to the conductor and meet ground, basically allowing us to confirm 100% coverage of that material, which is, because it's non-conducting, we're the only manufacturer that's allowed to do this and able to have 100% continuity testing of that material. Due to its non-conducting properties, it actually reduces electrical stress at the conductor insulation interface, right? Semiconducting conductor shields do not actually lower stress. They only even out the electrical field lines around that conductor. A non-conducting layer will actually reduce that electrical stress going into the insulation. A little overview of the electrical properties of this material. To low conductivity, moderate dielectric strength, high dielectric constant material. And you can see it compared to other materials on this chart to the right here. On the bottom left, we have a couple graphs showing electric field stress with a 1 mil and 5 mil protrusion at 5 mils and 20 mils from the interface. You can see the blue line is the PermaShield, the red line is the semicon. From the 5 mils, with a 1 mil protrusion, you can see the stress is greatly reduced. With the 5 mil protrusion, you can really see the impact of having that stress reduction at 5 mils from the interface. And then on the right side here, you can see a voltage contour showing the smoothness and the impact that the electric field lines in a PermaShield to semicon, the differences between them, right? So with that PermaShield, we're really not only just smoothing out those electric field lines, but we're also reducing that stress. Just a quick break to see if we have any questions so far. I know I just introduced a new concept with non-conducting conductor shield layer. So just want to see if there's anything so far, Kristen, in the Q&A.
Nothing in the Q&A tab, but we can also hold on to any questions. If you think of something later, please add it and we will ask it at the end. But you may continue, Matt. Thank you.
Moving along, we have Kerite's Discharge Resistant EPR, DR-EPR. In order to be qualified as discharge resistant, Kerite has to pass this ASTM test D2275. What happens is we have a 60 mil plaque of our discharge resistant material, and we pass 21 kV AC current through it to ground. It must withstand this bombardment of current for 250 hours without any erosion whatsoever to be considered discharge resistant. We have to do this on a monthly basis. In the bottom left here, we have other materials that have gone through that same testing in order to show the differences between discharge resistant EPR and other competitor materials, right? XLPE failing after 45 hours, TRXLPE making a little bit longer at 80 hours, and then standard EPR does make it a little bit further, but does fail after 200 hours. With, of course, our discharge resistant EPR passing and not having any degradation whatsoever at greater than 250 hours. Internally, we are running some tests to failure on this. We've exceeded 2,000 hours, and we're going to push it to failure to see how long we can really take this material, how far we can push this material to really see how discharge resistant it is, right? We boast a lifetime warranty because of the PermaShield and discharge resistant material in tandem, right? They really allow for a robust material. Some highlights about the discharge resistant material, besides being immune to partial discharge. It's known for its high flexibility, long-term stability in wet environments. Kerite did cut its cloth in subsea, so we have a nice long history of wet environments and the cable's robustness there. Improved thermal characteristics, and again, these materials are recognized by the main industry standards AEIC, ICEA. Another quick break. I know that was a new introduction again, Kristen.
Oh, no, we do have a question, and then also maybe if we can slow the pace down just a little bit, because this is some new information for some people. But the question was, are there different manufacturing routine testing requirements between discharge-free EPR versus discharge-resistant EPR cables covered by this cable standards?
Kristen. Yeah, so Kerite discharge resistant EPR has to meet the same requirements that ICEA, AEIC lays out, but we do have to do a couple extra tests as well. The main one being what was just covered here, which is this ASTM laid out test, ASTM D2275. This is the main one. This is done on a monthly basis, and it continually qualifies the material as discharge resistant. That's the main one that I want to cover. Both the discharge resistant EPR and PermaShield are recognized by AEIC, ICEA. And again, we have to do full qualification reports as anyone would in the power cable industry. The only thing that we're omitted out of because of this, and maybe not the only thing, but the main thing is because of the discharge resistance and the immunity to the effects of partial discharge, we're exempt from partial discharge testing. We're not worried about partial discharge whatsoever in the material. It's not going to break down. We have proven that through hours and hours and hundreds of hours of partial discharge bombardment or a similar environment, and the material doesn't break down. So the industry standards have made us exempt from those requirements. Moving along to our insulation shield options, due to the discharge resistant properties of our insulation, it allows us to have a thermoplastic free strip insulation shield. When I say it, I mean the industry standards, right? Because we're not worried about any sort of air gap where partial discharge could build up between the insulation and insulation shield layer. We can have a thermoplastic layer there. This thermoplastic layer allows for very clean, simple, fast stripping of the insulation shield. Being thermoplastic, it's not bonded to the insulation. So with a couple quick scores, you can just pop it right off, right? It is noticeably quicker than having to peel back your typical bonded insulation shield. That being said, Kerite does offer a thermoset uh, insulation shield as well for the companies and customers that are still requiring that. But it is something to have a conversation about because it is really nice and easy for your splicers, for your terminators that are out there and doing these tens at a time, right? It's Kerite is made for field friendliness. That's what we like to boast. Why would you want this? One of the biggest causes of failures in the field is workmanship, right? Overhandling cable, having to cut too deep into your insulation shield and get nicking your insulation, causing some sort of defect in the insulation that wasn't intended or didn't happen at manufacturing, right? These small little errors from stripping the cable can cause major catastrophic breakdown in your cable. So having, one layer that's much easier to strip and handle does equate to a safer cable and a cable that's going to last longer in the field. Now, being a thermoplastic material, there are going to be some trade-offs. The industry standards only allow thermoplastic insulation shields for 90°C applications. So I do want to talk about some of the operating temperature trade-offs when operating at 90°C versus 105°C. We've seen an increase from utilities specifying 105°C rated cables in the recent past, with the perceived advantage of a higher operating temperature equals higher ampacity. But there are some trade-offs that aren't being discussed with that higher ampacity. We've done some thermal performance studies using SimCap across, with some cables as an example. And while we are seeing that there is about a 9% increase in ampacity, we're also seeing about a 25% increase in losses from the conductor. We also compared dielectric losses and concentric neutral losses at that 90 versus 105°C, and they were pretty negligible, but you are seeing a significant increase in losses across the conductor. Back this up, we also included some information from a NETRAC study in 2019, where they were testing connectors for 750 kc mil and 1/0 cables at varying increasing conductor temperatures. And looking at this table here, you can see as the conductor temperature increased, the connector for those cables greatly outpaced the conductor temperature. With 10% of 1/0 samples had to be removed during 90° cycling as a result of severe overheating, and 30% had to be removed at the end of 105°C. So we need to look at the bigger picture when we're talking about 90 versus 105°C. There's a lot more to consider than just pushing that ampacity. Another thing to consider, and this is only going to be for certain applications, but for direct bury installations, soil thermal stability is a huge piece that may or may not be being looked at, right? When you're operating at 105°C, that surface temperature of that cable can reach about 100°C in some instances. And at 100°C, the water, the moisture in that soil can turn to vapor and dissipate from the soil, right? Dry soil can have a 3 times higher thermoresistivity than moist soil, and that's going to greatly derate your cable. When you have that dry soil, right, you have those higher temps driving away the moisture. That's going to cause thermal runaway. The heat can't dissipate, and so the cable that you've now rated at that higher temperature, higher ampacity, you can cause severe overheating, which is then going to lead to cable failure. Again, a lot of information about operating temperatures here. Give you a second to absorb it all. Any questions, Kristen?
Do have some. I'll hold most for the end, but just one right now. What is the standard warranty on these cables?
Kerite has a lifetime of the installation warranty, meaning it's warranted from any sort of manufacturing defects for the lifetime of any installation. If you pull out that cable and try to use it somewhere else, that warranty is void. But, we have cables installed as early as the 50s, 60s using the discharge resistant EPR PermaShield system that are still in operation today. Now I'm going to talk about reduced diameter designs. As I mentioned earlier, Kerite's PermaShield reduces the stress going into the insulation, right? So that means that it has some insulating properties. With those two materials in tandem, we can reduce our diameters greatly for specific applications. The two layers together, right? Um, with the compact conductor, we can reduce our insulation thickness. We do that basing off of max stress calculations. Include, very commonly used flat strap neutrals or copper tape, and then we can also reduce our jackets, right? Since we can reduce that stress through the PermaShield, we can greatly reduce that insulation layer to thicknesses commonly seen in PILC cable, right? What is PILC? PILC is paper insulated lead cable. It was a three-conductor design all under one jacket with compact sector conductors and an overall lead sheath. Very common in the early 1900s in urban development and densely populated areas. It was very reliable for a very long time, but now it's been about 100 years plus, 80 years, and we're seeing oil leaks. We're seeing lead cracks. It's hard to find contractors and workmen that can fix this cable and splice it. Not only that, no one can find manufacturers making PILC cable anymore. Coupled with environmental groups pushing for lead to be removed from the ground, it's opened up a market for how do we replace this cable in a cost-effective manner. As I mentioned earlier, EPA pressure for lead removal, reduction in skilled workforce for lead wiping and fixing this lead cable. It is getting old, right? Did great for a long time, but it's time to replace this cable. So Kerite has the reduced diameter PILC replacement design. We're reducing our insulation, we're compacting that conductor, we're offering flat straps or metallic shield depending on your fault current needs, and then we can also reduce that jacket if necessary. This offering reduces not only the weight, but it reduces cost as you don't have to pull out conduits and dig in city streets. You can just pull in this replacement as a one-to-one to your PILC if you had it. Because it weighs less, we can also offer longer lengths on reels, and it has increased flexibility. There's no heavy lead bounding that cable together. Looking at three different options in front of you, right? You have our PILC cable to the left and your standard URD cable to the right, and right in between is the Kerite reduced diameter option. We can get within 5% of that original PILC diameter. Again, we use three cables triplex together in a trefoil design, and we're almost half the weight, and again, 5% of that original diameter. So you don't have to worry about digging up city streets, and putting in new conduit. You can use that original conduit you already had, pull it in, and it's almost one-to-one to that PILC cable. Just to highlight one more time, less expensive than replacing entire duct systems, digging up city streets, no lead sheath. There's no concerns about lead getting into your water supply or having the EPA breathing down your neck. We're not using oil impregnated paper, extruded dielectric, which is commonly found. And today's manufacturers are just not making that cable. We're not monitoring lead in the blood like we would need to if we were manufacturing with lead. It doesn't require specialized skills to use this cable. Little summary of Kerite benefits. It is the power cable designed for the field, right? Reducing stresses. It's flexible. It's great in wet environments. It's immune to partial discharge, which is thought to be one of the most um, uh, the highest cause of breakdowns in cable outside of of workmanship errors. And it has a long life and reliability. We boast a lifetime warranty for a reason. We believe in this product. We have cable on the ground for since the late 50s, 60s, even older without the discharge resistant EPR PermaShield combo. So we really, believe in this product, and I hope you had a good idea of what this product can offer here from this short webinar, but please reach out with any questions. Thank you for your time.
Thank you, Matthew. Before we get to questions, just a couple of things. So if you would like to receive a certificate of participation for today's webinar, you can email me at kvanderwall@marmonutility.com. And also, we had a couple of questions of if this is being recorded and if they can get a copy of the presentation. Yes to both. You'll get a standard follow-up email from this webinar, but I will follow up to everyone who has registered, providing that link of the recording, as well as a PDF version of this presentation. Now we will get to the questions. So the first one is, Matt, what voltage levels have testing been performed on in regards to discharge resistant testing?
The discharge resistant testing, I think we're referring to the qualification that we have to do. That is done at 21 kV AC. That's a standard test dictated by ASTM. I might tag in my colleague, Mike Rainville, to discuss if there's any reasons why we don't do that at any other tests, but it's meant to, cover a large swath of, it tells about lower voltages, and it does a pretty good job of explaining how the material will react at similar voltages around that area. Mike, do you have more to add?
So my only comment on that is a standard sample thickness to represent, a uniform thickness and a standard voltage to keep it consistent from month to month.
All right, the next one. Is the thermoplastic insulation shield more susceptible to deformation or indents from neutrals?
No, no, actually it's not. We've actually seen the opposite. It we still have to meet the neutral indent requirement set by ICEA. So even if it was to be more or less susceptible by that by the neutral, we would still have to meet the ICEA requirement. So we're managing that internally, and it's not something the end user has to worry about.
Great, thank you. Next, was the NETRAC testing done on copper conductors or only aluminum?
It's a great question. I'm going to have to follow up for that one. I don't have that right in front of me. But I will get that to the individual asking that question.
Next one is, do you discharge test each cable reel that you ship out of your facilities?
We do not. No, we are exempt from the requirement for partial discharge testing due to this qualification test mentioned earlier, right? This qualifies the material as discharge resistant. And once we pass this, we know that that lot of material is not going to be damaged by any sort of partial discharge that might be present in the material. We understand that discharge free allows up to 5 picocoulombs. We're not worried about any partial discharge that may be present in the material. So we don't test for it because we know the material is not going to break down in the presence of it. That being said, we still have to meet ICEA, AEIC standards for any sort of voids in the material. So we're still, we still have guards in place to make sure we don't have excessively large voids that could have excessive partial discharge. So there are still checks in place to make sure we're not having excessive partial discharge in the material. But again, the material is not going to break down if there were or were not any sort of partial discharge.
Great, thank you. Next question. How do pull lengths for EPR compare to the PILC already in the ground? That is, they're asking, can we use the same splice box locations?
This is a very good question. I am going to have to do my research on that one before I speak on that.
Perfect. We can respond in writing post-webinar for
It's a
this.
great question, though. I like that.
Next question, is Kerite the only cable manufacturer using a discharge-resistant cable design?
To my knowledge, we're the only ones using the discharge resistant theory. Everyone else is a discharge free. They have to meet that 5 picocoulomb max requirement. Um, yeah, we are unique in the industry.
Thank you for that. And looks like our last question that we have right now, unless anyone has anything else to add to the Q&A tab, is how long has Kerite's current insulation system been in service in the field?
So the PermaShield discharge resistant materials were first introduced in the late 50s, commercially available in about, I think, 58 to early 60s. Um, so, uh, 70 years.
Thank you very much for that. I'll take one more look. And all right, if anyone has any questions that they think of, please feel free to reach out and email me. We will follow up in writing to those who I have responded as such. Thanks for joining today. And Matthew, thank you for the great presentation.
Thanks, everyone.